Hello everyone, welcome back to Tales of Chemistry. So the previous episode, we discussed about ideal as well as non-ideal solutions. Today we are starting with colligative properties. So what are colligative properties? These are the properties of dilute solutions, and in this properties or these properties depend only on the number of solute particles but not on the nature of solute particle. So this can be asked as give one word for kind of questions. Properties of very dilute solutions which depend only upon the number of particles of solute molecules or number of solute particles and not on the nature of solute particles. Such properties are called colligative properties. We need to study about 4 colligative properties. The first one is relative lowering of vapor pressure. So, what is this relative lowering of vapor pressure? All right. First of all, vapor pressure of a solvent gets reduced after the addition of a non-volatile solute into it. It's a fact, it's an experimental fact that the vapor pressure of a solvent reduces after the addition of a non-volatile solute into it. Now, if P naught of solvent represents the vapor pressure of pure solvent and P of solution represents the vapor pressure of solution, then by this word lowering of vapor pressure, we mean P naught of solvent minus P of solution. Vapor pressure of solvent minus vapor pressure of solution. That is what we mean by lowering of vapor pressure. Then what will be relative lowering of vapor pressure? Relative lowering of vapor pressure is lowering of vapor pressure by the vapor pressure of pure solvent. That is P naught of solvent minus P of solution by P naught of solvent. So that is called, this expression is called relative lowering of vapor pressure. But in Raoult's law, we have studied that this particular term, P naught minus P by P naught, is equal to the mole fraction of the solute. So now, relative lowering of vapor pressure is equal to mole fraction X of solute, mole fraction of solute. How do we calculate mole fraction of the solute? It is number of moles of solute by total number of moles. Number of moles of solute by total number of moles. Total number of mole is nothing but number of moles of solute plus number of moles of solvent. Okay, now I'm once again writing P naught of solvent minus P of solution by P naught of solvent, that is relative lowering of vapor pressure, is equal to N of solute, number of moles of solute by number of moles of solute plus number of moles of solvent. But if your solution is very dilute, okay, if your solution is very dilute, so I'm stressing on that, very dilute. Yeah, amount of solute is negligible when compared to the amount of solvent. Like you are taking about 100 gram of the solvent, but the weight of solute is 5 gram or less than 5 gram. So let's call that as very dilute solution. In very dilute solution, you can ignore N of solute in the denominator. Therefore, the present expression becomes N of solute by N of solvent. So in the denominator, I ignored that N of solute just because the solution is a very dilute solution. Now, how do I calculate N of solute? N of solute is calculated by dividing weight of solute by molecular mass of solute, right? N of number of moles of solute is weight of solute by molecular weight of solute. N of solvent is weight of solvent by molecular weight of the solvent. Okay, now I'm taking the reciprocal of the denominator here and multiplying it with the numerator. So numerator is W of solute by molecular mass of solute into reciprocal of the denominator M of solvent by W of solvent. So this is what now we use for calculating the relative lowering of vapor pressure. Relative lowering of vapor pressure is weight of solute into molecular weight of solvent by W of solute, molecular weight of solute into weight of solvent taken. But remember, if your solution is not a dilute, then you will have to keep this N of solute in the denominator also. You will get more clarity when we do the numericals. Now, second colligative property that we should discuss is elevation in boiling point. Elevation in boiling point. Now, what is boiling point? Boiling point of a solution is the temperature at which the vapor pressure of the solution or the liquid, solvent also, right? So, the vapor pressure of the liquid becomes equal to the atmospheric pressure. When the vapor pressure of a liquid becomes equal to the atmospheric pressure, that liquid will start to boil. That temperature is called boiling point of the liquid. Now, vapor pressure of a solution is always less than that of the solvent. Read this again. Vapor pressure of a solution is always less than the vapor pressure of solvent. So what will happen? Boiling point of the solution will be greater than, higher than. Boiling point of the solution will be higher than the boiling point of solvent. This is called elevation in boiling point. Meaning of this term, elevation in boiling point is boiling point of solution is greater than the boiling point of the pure solvent. Okay, now the difference in boiling point of solution, that is T of solution minus T of solvent. Difference between boiling point of solution and the solvent is called elevation in boiling point. All right. The difference in boiling point of solution, T of solution, and solvent, T of solvent, is called elevation in boiling point. So hereafter we represent elevation in boiling point as delta TB, where B stands for boiling. Delta TB is equal to T of solution minus T of solvent. And I'm skipping that experiment here. I'm just presenting the result of the experiment. Yeah. So experiments have proved that delta TB is equal to a constant Kb into molality of the solution. Delta TB is equal to a constant Kb into molality of the solution of the liquid. Now, what is Kb? Kb is called molal elevation constant or ebullioscopic constant. Molal elevation constant or ebullioscopic constant. And now we can substitute for molality in the previous formula. Molality is number of moles of solute into 1000 by weight of solvent in grams. I had to take this 1000 because I'm expressing weight of solvent in grams. Okay. Now, instead of N of solute, number of moles of solute, now I'm replacing it by weight by molecular weight. So, instead of N of solute, I have now written W of solute into 1000 by M of solute into weight of solvent. You are encouraged to by heart this formula. Delta TB is equal to Kb into W of solute into 1000 by M of solute into W of solvent. Avoid learning that W1, W2, etc. Learn it like this so you are never confused. Okay, so the second colligator property, once again, is the elevation in boiling point. First of all, we should know what is boiling point. Second, boiling point of a solution is always greater than the boiling point of pure solvent. This difference in boiling point is called elevation. Elevation in boiling point delta TB is equal to a constant into molality. That constant is specific for each solvent, okay, at a particular temperature. And the value of Kb will be given to you in the numerical. You don't have to by heart the Kb value because you don't know which solvent is given to you, right? So, finally, we substituted for molality. We got a new expression. Delta TB is equal to Kb into weight of solute into 1000 by molecular weight of solute into the weight of solvent. Now, let's move on with the third colligator property, which is depression in freezing point. Freezing point is the temperature at which vapor pressure of the solid, like after the liquid freezes, it becomes a solid, right? So, vapor pressure of the solid and the liquid, they need to be in equilibrium, are the same. So, freezing point is the temperature at which vapor pressure of the solid and the liquid are the same. Now, when you add a solute into a liquid, vapor pressure of solution is lesser than the vapor pressure of the solvent. Because of the same reason, the solution freezes at a lower temperature than that of pure solvent. So, write this down. This is a very important point, that vapor pressure of solution is lower or it is lesser than the vapor pressure of pure solvent. Difference in the freezing point of pure solvent and the solution is called depression in freezing point. Again, note this fact as well. Delta TF is T of solvent minus T of solution, whereas delta TB was T of solution minus T of solvent. Final expression delta TF is KF into molality. Here I substituted for molality just like the previous case. So I'm not explaining this. KF into weight of solute into 1000 by molecular weight of solute into weight of solvent. That was just the equivalent for molality. What is KF? KF is called molar depression constant or cryoscopic constant. Even the KF value will be given to you. KF value will be, with the unit, it will be given to you. The last colligative property which we need to study is osmotic pressure. Before we learn osmotic pressure, we must know what is osmosis. This itself can be a 1-mark question. The flow of solvent particles from the less concentrated solution to the higher to a higher concentrated solution through a semi-permeable membrane. What is the first point that we are noticing? Semi-permeable membrane is required for osmosis. Also, solvent is flowing. Okay, solvent is flowing from less concentrated solution. Less concentrated solution meaning the dilute solution to a higher concentrated solution. So from dilute solution to concentrated solution, only the solvent will be flowing through a semi-permeable membrane. That movement is called osmosis. Flow of solvent from dilute to concentrated solution through a semi-permeable membrane. It is called osmosis. Osmosis has to be differentiated by an identical term, that is diffusion. Sometimes, we get confused between these two terms. Now, so here are the differences between osmosis and diffusion, which can be a 2-mark question. Give 2 differences between osmosis and diffusion. Now, osmosis, we just studied the flow of molecules, solvent molecules, is from the dilute solution to the concentrated solution. So here I have written flow of solvent molecules from their higher concentration. Solvents a higher concentration, which is once again the dilute solution, to the lower concentration. Solvent is less in concentrated solution. So solvent is flowing from dilute solution to concentrated solution through a semi-permeable membrane. Solvent is flowing from dilute to concentrated solution through the semi-permeable membrane. This is called osmosis. Whereas in diffusion, you don't require a semi-permeable membrane. And here the solvent as well as the solute molecules are passing. So every particle can flow through, or not flow through actually, they get mixed with each other. The solvent as well as the solute particles get mixed with each other, move directly without a semi-permeable membrane. That is called diffusion. Osmosis is an exclusive property of solutions, whereas diffusion can happen in solution as well as in gases. Diffusion takes place in solutions also in gases. Osmosis can be reversed or it can be stopped. Yeah, you're aware of this RO in water filters. It is written reverse osmosis, RO. So that tells us osmosis can be reversed. Osmosis can even be stopped, whereas diffusion cannot be stopped or reversed. Okay, so osmosis and diffusion are two different properties. We must know the differences between these two. Here are the differences. Please write this down and study that. Now, so we understood what osmosis is, how is it different from diffusion. But what is osmotic pressure? Now, diagrammatically, if we represent osmosis like this, I have taken a tank. At the center, somewhere at the center, I have taken the semi-permeable membrane. And on one side of the semi-permeable membrane, I have taken dilute solution, and on the other side, I have taken concentrated solution. So osmosis is when the solvents are passing through the dilute solution to the concentrated solution through the semi-permeable membrane, right? That is osmosis. Now, on the wall of the semi-permeable membrane, from the concentrated solution side, yeah, if we are applying a pressure, okay, in the direction opposite to the flow of the solvent particle, in the direction opposite to the flow of the solvent particle, that is from the concentrated solution side, if we apply pressure, so that this pressure just stops the flow of particle. It is just sufficient to prevent osmosis. Such pressure or that pressure is called osmotic pressure. The minimum excess pressure which is required on the higher concentrated solution side in order to prevent the flow of solvent particles, in order to prevent the flow of solvent particles towards the concentrated solution through the semi-permeable membrane is called osmotic pressure. Now, if you cannot memorize this as it is, you can just write the pressure, okay, which just stops. Pressure which is just stopping the process of osmosis is called the osmotic pressure. Also, right, this is applied on the concentration solution side so as to prevent the flow of solvent from dilute to concentrated solution. So instead of in one sentence, you can write it in 2 or 3 sentences. Okay, so that is osmotic pressure. Now, osmotic pressure of a solution, of a solution can be compared with ideal gas equation. Hope you remember PV is equal to nRT, which we have studied in 11th grade for ideal gas. Here, for solution, this is applicable only when your solution is very dilute. It is seen that in very dilute solution, the solute particles behave like gaseous particles. Solute particles behave like gases when the solution is very dilute. Therefore, instead of PV is equal to nRT, we consider it as pi V is equal to nRT, where pi is osmotic pressure, V volume, N number of moles, our ideal gas constant, universal gas constant. T is temperature of the solution in Kelvin scale. Now, pi is equal to N by V RT. What is N? Number of mole. What is V? Volume in liters. So, N by V can be considered as the concentration of the solution. We can write the above relation as pi is equal to CRT, where C is the concentration of the solution, number of moles present in a particular volume, concentration of the solution. Here certain conditions are there. V has to be in volume and T is in Kelvin. R is universal gas constant. So the value of R, correct value of R is to be taken. Since we take volume in liter, pressure in atmosphere, then temperature in Kelvin, here the value of R will be 0.0821 liter atmosphere per Kelvin per mole, right? Reason is our temperature is in Kelvin, pressure is in atmosphere, and volume is in liters. So that is the fourth colligative property, which is osmotic pressure. That's all in this video. Stay tuned for more videos. Thank you.